parallelism of data access.
Are there different ways to partition?
Yes. You can partition it completely, meaning every single element becomes a separate register, maximum parallelism but uses lots of registers. Or you can partition by block, creating fewer, larger banks. Or cyclically, distributing elements round-robin style across banks. Each has different trade-offs in area and how access patterns align.
So the critical insight here, you said, is memory architecture first.
Absolutely. You must think about how your data is stored and accessed, and use partitioning to provide enough bandwidth before you try to max out parallelism with pipeline or unroll. Otherwise, those compute optimizations are often completely ineffective. Fix the memory bottleneck first.
Makes perfect sense. Okay, another big one, data flow optimization. This sounds like parallelism at a higher level, task level.
Yes, this is about enabling parallelism between coarser-grained tasks, typically between different functions or different loops in your code.
So creating a bigger pipeline, like a pipeline of functions.
Exactly, a macro pipeline. You apply the data flow directive to a region of code containing, say, a producer function loop and a consumer function loop.
And the tool connects them.
The HLS tool automatically infers and inserts FIFO channels, first in, first out queues between these processes to stream data from the producer to the consumer.
So they can run concurrently.
Yes. The producer can start working on the next piece of data while the consumer is still processing the previous one. It creates this coarse-grained pipeline, significantly improving overall system throughput, especially for streaming applications.
Very powerful. We should also quickly mention interface, right? For connecting to the outside world.
Yes, the interface pragma is crucial. It tells HLS how to implement the ports of your top-level function, what physical interface protocol to use, like AXI4 Lite for control status registers, AXI4 Stream for streaming data, or connections to single memory ports, BRAMs, etc. This automates creating those standard interfaces.
And inline we touched on, removing function hierarchy. Are there other, maybe more advanced optimization techniques people use?
Definitely. For memory, especially interacting with slow off-chip DRAM, local buffering is key.
Copying data on chip first.
Right. You read a chunk of data from slow external memory into fast on-chip buffers, usually BRAMs. Then your core HLS logic processes it from the fast buffer, reduces latency dramatically.
You want to transfer those chunks efficiently.
Yes, using AXI burst transfers. HLS tools can often infer burst transfers automatically from things like memcall calls or simple loops accessing contiguous memory blocks, maximizing the efficiency of that off-chip to on-chip data movement.
Okay, and this one is really cool. Arbitrary precision data types, not just int or float.
This is a fantastic advantage of HLS for hardware. Standard C++ types have fixed sizes, 8 bits, 16, 32, 64, but hardware can be built with any bit width.
So if I only need 10 bits for calculation...
HLS provides custom types, like a printW or sintw, where you specify the exact bit width W needed, so you can declare an uphunt 10. The tool then generates hardware operators adders, multipliers that are precisely 10 bits wide.
Instead of using a 16-bit or 32-bit operator, wasting resources.
Exactly. It leads to optimally sized hardware, saving significant area and power. Hugely important for resource-constrained designs, especially in AML with quantization.
Yeah, you mentioned LLMs are even being used to suggest optimal bit widths now.
It's an active research area, using ML to analyze the value ranges and suggest the minimum required bit widths automatically. Very cutting edge.
And how about structuring code differently for trade-offs?
Yeah.
You mentioned inline. What else?
Well, directives like loop merge can combine adjacent loops, reducing the overhead of loop control logic. Loop flatten can take nested loops and collapse them into a single loop.
Why would you do that?
It can sometimes allow you to apply a single, more efficient pipeline directive to the entire flattened loop structure, potentially increasing overall throughput compared to pipelining the inner and outer loops separately.
Interesting trade-off. And you can also explicitly control resource sharing.
Yes, using allocation directives. For instance, you might know you have a very area-constrained design and multipliers are expensive. You can tell the tool limit 1 for multiplier instances for a specific function.
Forcing it to use only one multiplier, even if more could run in parallel.
Right. It forces resource sharing, saving area, but it will likely increase the latency because operations might have to wait for that single multiplier to become available. It's an explicit trade-off you make.
So many levers to pull. Okay, you've run synthesis with your code and pragmas. The tool spits out reports. How do you make sense of them? You said they're diagnostic maps, not just scores.
They absolutely are your hardware's health check. You need to learn how to read them.
What are the first things to look at? Performance metrics.
Yes. First, latency. That's the total number of clock cycles for one complete execution of your function or loop. If your goal is low latency, this is your key metric. You target reducing it, often with unrolling.
Okay, total time. Then the other big one, initiation interval 2.
2, critical for throughput. Again, it's the number of cycles between starting new iterations or accepting new inputs. Lower is better. 2i1 is the goal for maximum throughput.
And if the 2 is high, like 5 or 10?
That immediately tells you there's a bottleneck somewhere. The design can only accept new data every 5 or 10 cycles. Something is limiting the pipeline.
Do the reports break this down, like per loop?
Oh, yes. Good reports give you detailed latency in 2 figures for every single loop, and often every function call within your design. This helps you pinpoint exactly where the performance bottlenecks are located in your source code.
Okay, performance metrics understood. What about resource utilization reports? Are those the final numbers?
No, and that's crucial to remember. The HLS reports provide estimates of the physical FPGA resources.
LUTs, FFs, BRAMs, DSPs.
Exactly. Look up tables for logic, flip-flops for registers, block RAMs for memory, DSP slices for math. These estimates are usually pretty good, but they are not the final numbers.
Why not?
Because the final placement and routing steps done by downstream tools like Vivado or Quartus can have an impact. Sometimes routing congestion might mean the final implementation uses slightly more resources or fails timing. The HLS report is your early guide.
Got it. Estimates, not guarantees. Now, to understand the why behind those latency and resource numbers, you mentioned graphical viewers.
Yes, these are incredibly helpful diagnostic tools. The schedule viewer is often the most illuminating.
What does it show?
It gives you a visual, cycle-by-cycle, Gantt chart-like view. It shows which operations are scheduled in which clock cycle and, critically, the dependencies between them.
So you can literally see the flow of execution over time.
Exactly. And you can usually easily identify the critical path. That's the longest chain of dependent operations through your design. The length of the critical path directly determines your minimum possible latency.
And it points you right to the C++ code causing it.
Good viewers will link directly from the operation in the schedule back to the specific line of C++ source code that generated it, so you know exactly what to optimize.
Very powerful. What about the dataflow viewer for those dataflow optimized designs?
Right. If you've used the dataflow pragma, this viewer visualizes the concurrent processes, your functions or loops, and the FIFO channels connecting them.
What can you learn from that?
You can see the depth of the FIFOs, how much data is buffering between stages. More importantly, you can see if there are stalls. Is the producer process waiting because the consumer is too slow? Or is the consumer waiting for the producer? It helps you balance the throughput of the different stages in your macro pipeline.
Balancing the assembly line. Makes sense. And for system-level stuff, a timeline trace.
Yes, especially when you have HLS kernels running on an FPGA interacting with a host CPU. The timeline trace shows the activity of both the CPU, host software, and the FPGA HLS kernel over time.
What kind of problems does that reveal?
It's great for spotting idle periods. Is your super-fast HLS kernel spending most of its time just waiting for the CPU to send it data or waiting to write results back?
Highlighting system-level bottlenecks, not just the kernel itself.
Exactly. It prompts system-level optimizations. Maybe you need double buffering so the CPU can prepare the next data chunk while the kernel processes the current one, overlapping communication and computation.
So it's really this feedback loop. Report identifies a problem. High latency, high 2 resource spike. Viewer helps diagnose the root cause. Critical path, FIFO stall, idle time. That leads to an optimization hypothesis. You need a pipeline in this loop, partition that array, add buffering. You apply the pragma or restructure code, rerun HLS, repeat.
That is precisely the iterative HLS optimization workflow. Analyze, hypothesize, modify, reevaluate.
Okay, HLS is clearly being used. What does the actual tooling landscape look like today? Who are the main players?
It's largely dominated by the big FPGA vendors, as you might expect. For AMD, formerly Xilinx, the main tool is Vitis HLS.
Vitis HLS. That replaced the Vivado HLS.
Yes, it's the successor. It integrates into their whole ecosystem, the Vivado design suite, if you want to generate traditional RTL IP blocks.
Okay, standard hardware flow.
Or the Vitis Unified Software Platform if you're developing CC plus OpenCL kernels for their accelerator cards, targeting more of a software developer flow.
And Vitis HLS has libraries and features.
Oh yes, Rich C++ libraries with things like those arbitrary precision types, a pint, streaming data types, hls.stream, task parallelism, hls.task, a very comprehensive set of pragmas for optimization. And it naturally targets AXI interfaces. The philosophy is quite software-centric.
Okay, AMD Vitis HLS. What about Intel, formerly Altera?
Intel's main offering is the Intel HLS compiler. It's tightly integrated into their Quartus Prime FPGA design software.
Similar capability.
Broadly similar, yes. It supports standard C++ air, includes features to help automate C++ test bench generation, uses its own set of pragmas, often specified differently but achieving similar goals, and typically infers their Avalon interface standard instead of AXI.
And generates reports with graphical views, too.
Yes, detailed HTML reports with schedule viewers and other analysis tools, much like Vitis HLS.
So these tools, Vitis HLS and Intel HLS compiler, they're not interchangeable, are they?
Not at all. Choosing one vendor's tool usually means committing to their entire hardware ecosystem, their FPGAs, their IP libraries, their specific design flows, their interface standards, AXI versus Avalon.
So porting HLS code written for an AMD FPGA to an Intel FPGA or vice versa is hard.
It's non-trivial.
Yeah.
You'd likely need significant code changes due to differences in the HLS libraries, uppaint versus accent, the pragmas, syntax and behavior, interface handling, and potentially underlying architectural assumptions the tools make. It's not just a recompile.
Good to know. Are there other tools beyond the big two? Open source? Academic?
There are. Siemens EDA has Catapult HLS, which is a well-regarded commercial tool that's vendor agnostic. There are open-source research platforms like Bamboo. There are specialized tools like SCCL for System-C to RTL, and lots of academic research exploring HLS, sometimes even using other languages like Rust, though C++ remains dominant.
Okay, let's talk about where HLS really shines, the sweet spots. What are the key applications where it provides the biggest bang for the buck?
HLS really excels in areas that are computationally intensive, algorithmically complex, and especially, as we've discussed, data flow intensive.
Like processing streams of data.
Exactly. The traditional sweet spot has always been image, video, and signal processing. Think filters, convolutions, FFTs, codecs. These algorithms map beautifully to the pipelined, streaming hardware architectures that HLS is really, really good at generating.
Makes sense. You also mentioned a really compelling case study for network acceleration, something about receive-side scaling.
Ah, yes, the Bitware RSS case study. It's quite striking. They needed to implement an RSS hashing function for a 100 gigabit per second network interface card.
Okay, high-speed networking.
They did it both ways, manual RTL and HLS. The HLS version was completed in just 1 week.
1 week, and the RTL?
The manual RTL version took 1 month, so 4x faster development time with HLS.
Okay, that's the productivity gain we expect.
Yeah.
But there was more.
Here's the kicker. The HLS-generated design actually used significantly fewer FPGA resources. It used about 2,400 configurable logic blocks, CLBs. The manual RTL used over 44,000 CLBs.
Wow, that's counterintuitive. HLS used less hardware and was faster to develop.
In that specific case, yes. It really showcases how the automated exploration and pipelining capabilities of modern HLS tools can sometimes find more efficient implementations than a typical, perhaps rushed manual RTL effort. It challenges the old assumption that HLS always means bigger hardware. It's not just faster development. It can sometimes be better quality of results or QRR.
That's incredible. Really shifts the perspective. What about high-performance computing, HPC?
Another major area, FPGAs are increasingly used alongside CPUs and GPUs to accelerate scientific simulations, financial modeling, data analytics.
And HLS helps HPC experts use FPGAs.
Exactly. Many HPC domain experts are fluent in C++ or Fortran, but not necessarily Verilog or VHDL. HLS provides the bridge. It lets them take their complex algorithms, often already written in C++A, and offload the compute-intensive kernels onto FPGAs to achieve massive parallelism, both spatial parallelism from replicating units and temporal parallelism through deep pipelining.
So they can leverage FPGA power without becoming HDL gurus.
Precisely. It lowers the barrier to entry for hardware acceleration in HPC.
And then perhaps the hottest area right now, AI and machine learning acceleration. HLS seems like a perfect fit here.
It's arguably the fastest growing application area for HLS. AI algorithms, neural networks, deep learning are inherently highly parallel and compute intensive. Lots of matrix multiplications, convolutions.
Perfect for hardware acceleration.
Exactly. And HLS allows designers to create bespoke, domain-specific AI accelerators. Instead of using a general-purpose GPU or TPU, you can use HLS to build hardware tailored precisely to accelerate one specific AI model or type of model very efficiently.
So potentially better performance or power efficiency than general-purpose chips for that specific task.
Often, yes, especially for inference at the edge, where power and cost are critical. You can optimize the hardware exactly for the model you need to run.
And this is where those arbitrary precision data types become super important, right? Quantization.
Absolutely critical for AML. Full 32-bit floating point math is expensive in hardware. Many AI models can tolerate much lower precision, maybe 8-bit integers or even less without a significant drop in accuracy. This is called quantization.
And HLS makes this easy with types like a pint.
Yes, HLS lets you easily implement computations using these custom low-bit width fixed point types. Using 8-bit instead of 32-bit math dramatically reduces the hardware size for multipliers and accumulators, saving huge amounts of area and power.
Are there frameworks that help with this AI to HLS flow?
Yes, frameworks like HLS 4mm are specifically designed for this. They can take models trained in standard ML frameworks like TensorFlow or PyTorch and automatically generate HLS C++ code, often incorporating quantization, targeting FPGAs.
What kinds of models are being accelerated this way?
All sorts. Convolutional neural networks, CNNs, for image recognition, transformers for natural language processing, even large language models like variants of GPT-2 have been demonstrated running efficiently on FPGAs using HLS-generated accelerators. It's a very active field.
Okay, we've covered a ton of ground. HLS is clearly powerful. But let's address that ongoing debate. HLS versus traditional RTL. It's not black and white, right? What's the core trade-off?
Definitely not black and white. It's very nuanced. The fundamental trade-off, as we've touched on, usually boils down to productivity versus control.
HLS gives you speed.
Dramatic acceleration in the design cycle, verification cycle, and that amazing speed in design space exploration.
But you sacrifice that fine-grained, cycle-by-cycle, bit-level control you get with manual RTL.
Exactly. RTL gives you the ultimate control if you need to manually optimize every gate and every clock cycle. So it's often framed as, trading engineering time, less with HLS for potentially more hardware resources, sometimes with HLS, though not always, as we saw.
Right. Which brings us to performance and resource utilization quality of results, or QRR. There's still this persistent belief, especially maybe among older school hardware folks, that HLS is just inherently inferior, less performant, bigger area. How true is that today?
That belief definitely has historical roots, and in some cases, it can still be true. There was an example comparing a 9x9 convolution filter where the manual RTL took about twice the design time, but the final result was faster and smaller than the HLS version. That's the classic trade-off scenario.
Engineering time versus QR.
But then you have the bitware RSS example we discussed. HLS was 4x faster to develop and used dramatically fewer resources.
Showing the opposite.
Right. So the conclusion really is, it depends. For the right kind of application, especially data flow intensive ones, well-written, hardware-aware HLS code, using the right pragmas
can achieve comparable or sometimes, as bitware showed, even superior results to a typical manual RTL effort, especially when design time is critical and you benefit from that rapid architectural exploration.
The blanket statement, HLS is inferior, is really outdated now. Modern tools and methodologies are much, much better.
So given that nuance, how does a designer choose? When should you lean towards HLS?
HLS is generally the strong choice for those data flow-centric algorithms. Image video processing, signal processing, AML kernels, network packet processing functions.
Makes sense. What else?
It's ideal if the algorithm already exists in a high-level language like C or C++L. It's great for rapid prototyping and when that architectural exploration is really valuable. And of course, whenever time to market is the absolute overriding priority.
Get something working fast, explore options quickly.
Okay.
And conversely, when is traditional RTL still the king? Where does it make more sense?
RTL remains the better choice for very control-dominated logic. Complex state machines with intricate timing, arbiters, maybe CPU cores themselves, things where precise cycle-by-cycle control is paramount.
Okay, fine-grained control logic.
Also, for very low-level, cycle-accurate interfaces, think deep, complex DDR memory controllers. The timing there is incredibly sensitive, often requiring manual RTL implementation.
Right, where every picosecond matters.
And, naturally, for designs where you absolutely must squeeze out every last bit of performance or minimize every last logic gate, and you have the engineering time budgeted for that painstaking manual optimization.
The handcrafted approach for ultimate optimization.
Got it. So, looking ahead now, what's next for HLS? How is it evolving?
Well, the biggest trend is that HLS is moving solidly from being a niche tool to a mainstream design methodology.
It's becoming more standard.
Yes, it's learned from past attempts and failures, really focusing now on CC++ for data flow, integrating tightly with the main vendor flows. For many types of blocks, especially compute accelerators, it's arguably becoming the default design entry method, replacing manual RTL for those tasks.
That's a significant shift. Now, here's where it gets really futuristic. Machine learning for HLS design space exploration. Finding the best pragmas manually sounds incredibly tedious. It is tedious. That DSE space is huge. Exploring it, manually change, pragma, synthesize, check results, repeat takes ages.
So ML is automating that search.
Exactly. ML models are being developed that can predict the performance and resource usage of a given set of pragmas without running the full, slow synthesis process each time.
Wow. How does that work?
Techniques like Bayesian optimization or using graph neural networks, GNNs, trained on the code structure, can intelligently search the massive design space much faster than random guessing or manual iteration. Frameworks like AutoHLS have shown speedups of like 70x in finding good optimization settings.
70x, that's democratizing hardware design almost, making optimization accessible.
That's absolutely the goal. Automating one of the most complex and time-consuming parts of achieving high performance with HLS.
And the latest frontier, large language models, LLMs like ChatGPT, for HLS code generation and even fixing code.
Yeah, this is super cutting edge, but incredibly promising. People are training LLMs to take standard C++ code that isn't synthesizable. Maybe it uses recursion or dynamic memory.
The stuff HLS normally chokes on.
Right. And the LLM can automatically rewrite it into an equivalent HLS-compatible form.
That's amazing. Can they help with pragmas too?
Yes. They can suggest where to put pragmas like pipeline or array partition or even insert them directly. Often, this uses a technique called retrieval augmented generation, or RAG.
RAG. What's that?
It means the LLM doesn't just generate code from scratch. It retrieves known good, verified HLS code patterns or templates from a database and adapts them to your specific problem. This helps prevent the LLM from hallucinating incorrect or inefficient HLS code.
Using verified building blocks. Smart. Could we eventually just describe hardware in plain English?
That's the long-term vision for some researchers, natural language specification translating directly into optimized, synthesizable HLS C++ code. Still a way off, but the progress is rapid.
Wild. What about other programming models emerging, like SYCL or OneAPI? How do they fit in?
These are interesting. They aim for higher-level abstraction, trying to provide a single C++ programming model for performance portability across different kinds of hardware CPUs, GPUs, and FPGAs.
Write once, run anywhere optimized.
That's the ideal. SYCL, for example, can often use an HLS compiler underneath for the FPGA target. They provide a higher level of abstraction than raw HLS C++ bait.
But is there a catch for FPGAs?
The catch is that while they abstract away some details, achieving truly optimal performance on an FPGA still often requires writing your code in a hardware-aware style, thinking about data flow, memory access patterns, things that map well to the underlying HLS principles. The abstraction isn't magic. You still need to guide it for the best FPGA results.
Which brings us back to a crucial takeaway from all this. These HLS tools, the AI assistants. They're incredibly powerful, but they don't make hardware expertise obsolete, do they?
Not at all. That's perhaps the most critical insight to leave with. The best results, the highest performance HLS designs, consistently come from designers who understand the underlying hardware.
They know about pipelining, memory banking, data flow.
Exactly. They use that knowledge to write their C++ code in a way that explicitly describes an efficient hardware implementation. They guide the powerful automation tools, make those critical architectural trade-offs using pragmas and code structure.
So the designer's role is shifting.
It's definitely evolving. Less focus on the painstaking gate-level details of manual RTL coding, and more focus on being a high-level system architect, understanding the algorithm, understanding the hardware capabilities, making smart architectural choices, and letting the HLS tool handle the complex implementation details.
The need for hardware expertise isn't gone. It's just moving up the stack.
Perfectly said. Moving up the abstraction stack.
Wow. What an incredible deep dive. We've journeyed from algorithmic C++ all the way to physically optimized hardware using HLS. We've seen the huge productivity gains, the power of exploring architectures rapidly.
And that really exciting future being driven by AI and automation, constantly reshaping what's possible in hardware design.
HLS is truly transforming how we approach building digital systems. It's enabling iteration and specialization in ways that, frankly, were hard to imagine just a decade or two ago.
It's making custom high-performance hardware much more accessible to a broader range of engineers and researchers.
Which leads us to our final thought for you, our listeners. As AI and automation increasingly shape the tools we use, what new frontiers will you explore in this world of custom hardware? And maybe more profoundly, what does it even mean to be a hardware designer when the very definition of design itself is constantly evolving?
Something to definitely ponder.
We'll leave you with that. Thanks for joining us on The Deep Dive.